Good morning, calculus students. Today is an asynchronous learning day due to the MCA testing that's going on at Tartan. So please make sure you watch the videos. And if you did not watch the video from last Friday, there's an Ed Puzzle video. Check out the link from week 4, Friday folder, and go ahead and watch that as well. And that should give you a good idea of what we're focusing on for this unit. Here's a quick warm up. Give it a shot, and we'll go over it in a second or two. All right, problem number 1. We want to write the area of each of the following shapes. Well, they're both circles, so the big focus today is remembering what the area of the circle is, pi r squared, and that will give us this full area here. What if I have a circle within a circle? So I want to find the blue shaded region. Well, I always think of this as a picture equation. What are we doing? We're taking the area of the large circle and we're subtracting the area of the smaller circle. So the total area expression is going to be pi with the large area, so I'll use a capital R for that one, minus, so pi r squared, and then the white circle here has a smaller radius of r, so its area formula is pi r squared, but notice the difference between the capital R and the lower r. The only other thing I want to show you is that because we have two radii here, notice how both items have a factor of pi. Another way to write this is the radius of the large circle minus the radius of the small circle, and then multiply that by pi. And that will give us a representation of the area of this item. Now, in a little bit, we're going to refer to this item not as a circle, but as a disk. And then this item, we're going to refer to it as a washer. So today, our focus is solely on the disks. On Wednesday or Thursday, we're going to be looking at the washers. So here's our quote for today. It is better to walk alone than with a crowd going in the wrong direction. Let's take a look at our main idea here today. We're going to look at revolving a two-dimensional region around an x-axis, or a y-axis actually, to determine the volume that it sweeps out. Now, this is kind of a conceptual piece that we really kind of have to be aware of, and that's my goal to start, is just to get you to visualize this process, and then we'll worry about how we actually solve it using calculus. So let's take a look here quick. What if I take this region, now the region is bounded by the y-axis, the x-axis, and this function. So all I did was graph it, and I found that it hit 2 and 4. So now what happens if I rotate this? Well, if this reflects over, how high up am I? And actually, you know what? I just kind of made this problem up. If x was 0, yeah, that actually would work out perfect. So if I go over here and I reflect this, how far down is it going to go? Well, it's 2 up from the origin, so it's going to go 2 down. And then what if I pick another point randomly here? Okay, how far up is it? Well, we're not really sure, but if I reflect it down, it's going to be the same distance above and below. And if I do that for all the points, then I will get a symmetric curve to the way I did above. All right, now we've dealt with that. That's just a reflection over the x-axis. But what if the whole thing is not just reflected, it's rotated? And what does that mean? That means that if I took a point like this, it's going to actually hit spots above. Now this dotted line is not going into the left side of my graph. It's actually coming up off the page three-dimensionally, and then it's going to go behind it. Okay? And I don't love the curve of this. I might draw it differently. But this is going to come up off the page, so it's actually coming towards you. And then it's going to hit this point, and then the dotted lines means it goes behind the x-axis. It's a rotation. So what if I take this point and I bring it up off the curve so it's coming towards you, and then it comes back and hits this point, and then it goes behind. What if I kept doing that? I picked a point here, and I have it come up off the curve, It hits its reflected point, and then it goes back around. What does that actually create? It creates a three-dimensional solid that would shade in kind of the rest of this region. And I know this is kind of hard to see, but this would be my three-dimensional object. And I'll show you a better picture, but it looks like a cone, right? Cone kind of flipped on its side. So what are we going to do? Well, our goal is to take a piece of this. And when I say piece, what I mean is I'm going to start at a point, and we're just going to pull out a section. And actually, if you remember from geometry, if I take this shape right here, okay, picture that as like a sliver, we're going to pull it out and look at what's called the cross section. Now that cross section should be a perfect circle because of the way it rotated and the symmetry it has with the x-axis. So just as we did in the warm-up, this circle has a radius. And we can actually find the area of any circle is pi r squared. And the question today then is, what is that radius? Well, here's where it gets tricky. What is the radius? The radius starts at the x-axis and it goes up to the curve. So if this was right on the origin, its radius would be 2. But how do we know what that is? We have to look at the equation. So this is the length of the output of the function. It's the y value. So all I need to do is solve this for x. So if I subtract 4 and then divide, I'm going to skip some steps. Maybe I won't. I'll divide by negative. And then I'm going to take the square root. I like to write the y first. So we end up with the square root of, oh, actually, sorry. That should be positive, and then when I divide it, the x is negative. X is negative right here. So what is this? This function says whatever x is, here's the output. That's the length of the y value, which means that is our radius. Our radius is negative x plus 4. So I'm going to go to that radius and actually plug in negative x plus 4 under the square root. And then according to the area of a circle, it says take your radius and square it and times it by pi. Well, a little bit of algebra simplifies this out. So I get pi times negative x plus 4. Now, don't distribute. I'll show you why in a second, but notice, here is the area expression for this cross-section. That's basically this shaded area of this circle. Now, we still didn't answer the question of volume. Right? How do we find volume? Well, what is volume? Volume is the accumulation of every one of those circles added up. If I made a circle at every point possible, which there's an infinite amount of points, and there's an infinite amount of circles, right? If I picked this point and this point, connected it, you could see another circle there. Well, this volume is the accumulation of all the circles added up from 0 to 4, because we're rotating about the x-axis. So, how would we set that up then? Well, accumulation is the integral of the area with respect to whatever axis we're rotating about. So here I just put the dx. Okay. Now, we know a couple things, right? We know what the area is. We just found it right down here. The area function is pi times the radius squared, and sometimes the algebra simplifies this a little bit. Remember, pi is a constant, so it's going to float out. And then I have negative x plus 4 with respect to x. We're going to take the antiderivative with respect to x, and that is the accumulation of all the circles added up, starting at 0 to 4. Okay? Now, where do those bounds come in? Well, if I start at x equals 0, that's the first where the first circle appears. And then if I end at x equals 4, That's those same bounds we kind of looked at when finding the area under a curve. So I want you to pause for a moment, look at what we did. All of this is the new stuff today. Once you set up the integral, I'm going to assume that this is really friendly and you can solve that very quickly. So we won't go over time on how do we evaluate that integral, but I'll just do it here. Oops, this is supposed to be V. So what is volume? Notice how I'm leaving pi until the very end. I'm going to take 4, plug it in, and then we're going to subtract the 0. Now, if I put a 0 here, I'll get a 0, so I don't really have to put that out there. I do have to be careful because the way I wrote this is not technically correct. There should be parentheses between this, so the pi is on the outside. So then what is volume? Volume is the simplified version of all of this, so I'll do part of this in my head, but we get pi times, let's see, 16 times -1/2 is -8, plus 4 times 4 is 16, minus 0, and we get 8 pi. So that is the amount of three-dimensional space that this red piece will turn out to be. So there's one problem of us rotating about the x-axis. We're going to do 2 more today. Here's your main idea. If you want to pause the video and just kind of get this down, we're only looking at a disk method, which we talked about in the warm-up a little bit. That's just plain circles. So what's our main idea? Well, all of those circles added up is the accumulation. So it's the area with respect to x or y. It depends on what we're rotating about. And that's going to equal the volume. So what are our steps? First thing you need to do, sketch a graph. Find the area of the cross-sectional item. Well, today, our area is just going to be a circle. So when we say this area here, you know it's pi r squared. And really the challenge today is just identifying what is the radius. Once you have that set up, then you solve using any regular calculus methods we've learned. Let's look at a couple examples. I'm going to show you a couple things just to help visualize what's going on. I do not expect you to write this, but let's look at an example of a solid of revolution that turns out to be a right cylinder, which is generated by revolving the region bounded by a horizontal line, y equals a. So here's the line, y equals a. And a has to be greater than 0. So we're above the x-axis. We're also bounded by the x-axis, and then the lines x equals a and x equals b, and we're rotating about the x-axis. So that's where this curve comes from. So let's see if you can just visualize this. From the information that is given, right here, basically all of this, you get this item. You have the line y equals a, bounded by x equals a. Can't draw a straight line to save my life with this thing. X equals b, and the x-axis. So your original area is a rectangle function. Now, what happens if I rotate that? So here's where hopefully the visualization piece will come in. If I take this point and I rotate it all the way around the x-axis, how do I know it's the x-axis? They tell me. Right? Now notice, it doesn't say rotate right there, but it says up here, revolving the region around or about the x-axis. So we're going to rotate it around. So this point is going to come up. If I can draw this perfectly, I'm going to hit all this piece. And then here's the perfect reflection over the x-axis. And then the dotted line is the part that we aren't meant to see three-dimensionally. And there's one circle. Well, if I do the same thing here, I'll hit this point, and then we'll go and get our dotted line right there. And same thing, if I picked a point here, it would be the same thing. We'll come up until I hit its exact reflection, and then we'll go around the back. And notice, as bad as that all looks, what is each cross-sectional shape? It's a circle with the region pi, or the area of pi r squared. And what is the radius? The radius is always from the x-axis up whenever you're rotating about the x-axis. So whatever this equation was, which is y equals a, all of these radii here will have the same output. So this is a very friendly function. Your radius here is just a. Okay, let's look at another one. Again, we're just looking at visualizing this. What if I took a right cylindrical cone, and that is generated by revolving the region in the first quadrant bounded by the line y equals mx, where m is greater than 0. So notice that's linear. The x-axis and the line x equals h about the x-axis. So here's my view. If I just was graphing the region, okay, we did this in section 8.1. Find the area under the curve, right? So here's the line y equals mx. Here's the x-axis, and then here's some equation that's vertically up and down at x equals h. So here you can see this region. Now, what if I rotate it? Okay, and again, this is the key right here. We want to find this rotational piece. So what if I take a point here and I just rotate it down? Okay, it's going to come up off the page, and then it's going to go behind the x-axis and create a circle. So if I take another point here and I reflect it perfectly straight down, it's going to come up off the page, reflect back, and there's my circle. And if I take this point and reflect it straight down, that will come up off the page, make the circle, and then come back around. And you can see by rotating the original area under this curve, this green shaded area, by rotating it around the x-axis, it creates a cone. And what is it? It's a bunch of small circles starting here, circle, 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 and then it gets bigger, bigger, bigger. It's the accumulation. The volume is the accumulation of all those circles added together. So hopefully this helps paint a picture of what we're doing today. Here's one more. What if it's not a friendly function? Right? You can read this as much as you want, but what do we have? We've got a region that has a function f of x, right? We don't really know what this curve is, but it's definitely not a linear one. And then we're bounded by the line x equals a to x equals b and the x-axis. So what would this look like if I rotate it? Well, what we're going to do is we're going to take this blue curve and we're going to mimic it. It's not easy to do. I'm going to just picture a bunch of random points here on the line, and we're thinking, okay, how far am I away up? I'm going to go down. And then here, this one's a little closer, and then it starts to get further away, and then we get to the last point B, which is reflected over. So that's basically the curve that was given, reflected, and then we're going to draw our circle. All right, so I'll take a point here. I'm going to come up off the page and come to this point, and then we're going to reflect around. Okay, same thing here. I'll come up off the page, reflect around, and we'll keep going. Again, you don't have to do all of these, but hopefully this just helps paint the picture of what's this going to look like. So I'll do the last one. And that one you can kind of see because of the way I drew it, but notice all of those are circles that change in radius that make up the total volume. So what does it look like? If you can picture it, this is the first circle that we drew. And then there's a bunch of them here. Here's the second. Oh, I missed it. Something's going on with my pen. And there's kind of one in the middle. That's our cross-sectional area. So notice every single cross-sectional area today is just a circle. This image right here, we call it a disk. It's actually a disk with a height of dy dx. So the difference of x we're going to call dy dx. That's the thickness. We're going to picture the thickness being an infinitely small thickness. Okay, So hopefully that just kind of helps paint the picture. Let's look at two examples, and I think you'll get a really good feel for this. So what do we have to do first? We have to create a graph, right? Step one, create a graph so you know what you're looking at. Find the volume when the region between, this should be a square root all the way over, between the square root of x equals 4, and the x-axis is revolved around the x-axis. So now they're telling us which way to revolve around. But let's graph. So let's think of this. The square root of x. Well, what if x is 0? If x is 0, the square root of 0 is 0. So I'm going to have a point right here. And then what if x is 1? 1, 2, 3, 4. I know for sure I'm going out to x equals 4. And I know the square root of 4 is 2, so the highest I will go is 2. So what if I get over 1? Well, the square root of 1 is 1. The square root of 4 is 2. I'm just going to estimate my slope, or I shouldn't say slope, I'm going to estimate my curve to look like that. Okay? Now, let's reflect. So when I reflect, here the highest point I went is 2, so the lowest I'm going to go is negative 2. And we're going to have a point, instead of going up 2 here, to get this point, we'll go down 2. And instead of going up 1, we'll go down 1. And then I'm just going to draw the rest of that curve in. And if you're really good, this curve below should match perfectly the one above. And then let's picture that rotation. What does it look like if I rotate the top function, or the top one to the bottom? And then what if I pick this point here and I rotate it? That should be dotted. If I pick a random point, rotate it, and then there's my three-dimensional image. Now you don't need much. Once you get the idea, again, you don't get any points for creating your graph. What I want to do is I want to think of, what does a cross section look like? So if I pick out a cross section here, it's a circle. Okay. Now, that circle, picture that circle being shaded in. Maybe I'll use green. Well, what do I need? I need to figure out what is the radius, because my ultimate goal is to figure out what is the area of that circle, pi r squared. So now the question is how long is this radius from the x-axis straight up? Now notice, this is an arbitrary point, so I don't really know. What we want to do, though, is we want to say, well, the length is actually the same as the y value of the equation. So this function is y equals the square root of x. And any point on this curve, its vertical distance is the equation square root of x. All right, so there's my radius. So what we're going to do is we're going to actually plug that in. Area is equal to pi r squared, but the radius is the square root of x. And then we're just going to simplify because that'll make our lives easier. So square root and squared go away. Here's the area of the cross section. Now this represents any one of these infinite amount of circles that we have. Now, what is volume? Volume is the accumulation of the area with respect to, now why is it x? This is dx because we are rotating about the x-axis. Another way to think of it is think of how the circles are stacked up. The circles are stacked up from x equals 0 all the way to x equals 4. So when you're stacked up from left to right, you're referring to your x values. And that actually leads me to my bounds, right? Where was the first circle present? At here, right here at x equals 0. And where's the last circle present? Right here at x equals 4. Okay, so then volume is the integral of the area from 0 to 4 with respect to x. But notice our area we have right here, pi times x. So pi is a constant. I'm going to float that out, and we'll put an x there. That's all we have for new material. Everything else, you just do evaluate the integral once it's set up. My hint to you, leave pi alone until you do all your work. So I'm going to take the antiderivative of x. Now we're going to go from 4 to 0, and then we'll plug in 4. I'm going to say we plug in 0, but plugging in 0 gives me 0, so I'm not going to write much. And I'm going to do most of this in my head. 4 squared is 16, half of 16 is 8. So the volume is 8. Nothing crazy there. All right, final example. What if I rotate about the y-axis? Now we have to change the way that an item is presented. And sometimes that means we have to adjust how the formula is written. So find the volume of the solid of revolution generated by revolving the region bounded by the graph of y equals x to the third, the y-axis, and the lines y equals 1 and y equals 8. And then we are revolving about the y-axis. So you kind of have to read that carefully, right? It says find the volume of revolution by revolving the region bounded by all of this and then about the y-axis. So we're actually going about flipping it instead of the x-axis. Now we're going to go about the y-axis. All right, let's start off with a graph. Okay? And again, you don't need super accurate graphs here, but it's important to kind of understand what's going on. So what do I have? I've got the cubic function. If you remember that, you can kind of graph that quickly. If you don't, think about your x values. Okay? We're not going to go very far in the x values, but 1, 2, 3, 4, 5, 6, 7, 8. I do know I'm going to stop at 8 because it tells me I'm going to go from 1 to 8. So let's just plot some random points. If I plug in 0, if x is 0, my output is 0. What if x is 1? Well, the cube root of 1 is 1. What if x is 2? The cube root, or excuse me, the cube of 2 is 8. So that would come up here. And then here's the function. Right? You could draw it going up with an arrow if you want. You could even draw this, right? Because that's the cube root or the cube function. However, we don't care about anything other than what's set up by the regions, because it's also split up by the y-axis. And then we're going from 1 to 8. I'm going to go from 1 to 1 to 8, which means I really don't even need this part right here. You can leave it on there. There's no harm in keeping that. But there's my region that I need to revolve. Let's just make that appear a little different. There's the area. Now, we could find the area between this curve, right? That's what we did on the other day's homework. But what happens if I revolve that? Okay, now, when we say revolve, this time we're going about the x-axis. So I'm going to rotate it this way. Oh, sorry, y-axis. Misread that. So what do? I have 1 point that is 1 unit to the right. So let's estimate 1 unit to the left. And then I've got up here, when x is 2, I'm 2 units away from the y-axis. Let's go 2 in the other direction. And let's just connect that with that rough, smooth curve. Now, if I connect this, you can see that it's a kind of a bowl. And then this part will be dotted. Okay, if I connect any random point, like let's pick this point, if I reflect it over, and I draw my reflection this way, see the three-dimensional image that appears? What would its cross-section look like? Well, if I took this piece right here, its cross-sectional area is a circle. and then we have to figure out its radius. Now the tricky spot here, here's a hint. Because we're rotating about the y-axis, that means everything has to be written in terms of y. So I need to solve this so y is part of my equation, which means I'm just going to take the cube root, and there's the radius. So how do we find the length of the radius? The radius is now the distance from the y-axis straight over. So I need basically something to tell me that what is x, because this length from here to here is how far we go on the x direction. And that's what the equation is. It's the cube root of y. Okay, now we're going to write our area. Well, it's still a circle, pi r squared, but this time my radius is the cube root. Now remember, instead of the cube root written as the cube root of y, we could write that as the 1/3. And the reason why I do that is when I simplify, y to the 1/3 squared is really the same as y to the 2/3. Okay? Now, that's the area. That represents one of these circles. But remember, we have an infinite amount of circles added. And where does it start? It starts at the equation y equals 1. And the circles are added up vertically now. And we don't stop until we get to y equals 8, which are my bounds. So the volume is the accumulation of the area from the lowest bound to the highest bound. And then we'll just go ahead and put our area formula in. Remember, pi is our constant, so we get 2/3, and we have to be careful here. Notice everything is in terms of y. We rotated about the y-axis, so that's why it says dy. And now it's old calculus. Okay? This is just evaluate the integral. So I'm going to do that really quick. I'm going to add that creative form of 1. So I'll get y to the, this is 3/3. So that gives me 5/3 here, which I'll put a 3/5 out in front. And then we got to evaluate from 1 to 8. Okay? And again, leave your pi alone. Don't mix pi in here because it gets kind of confusing. So I get 3/5 times 8 to the 5/3 minus 3/5 times 1 to the 5/3. And remember that 5/3 is, when I think of the 5/3, I think of it as the 1/3, which is the cube root, to the 5th power. So in my head, I'm taking 8 to the cube root and saying that's 2, and then 2 to the 5th power, which is 32. And then the nice thing here, 1 to the any power is 1, so I get a 3/5 there. And then we just have to simplify. Think of that as 32/1. And if I do 3 times 32, we get 96. Over 5, and then minus 3/5. So then we get 96 minus 3 is 93 fifths, and then pi just pops in right at the end. And again, you could use your calculator to check this as an answer. All right, let's talk about common errors really quick on how people misinterpret problems like this. So one of the big things is the way the problems are written. You have to really read carefully. It says when we revolve the region, and then they don't tell us till the very end that it's going around the y-axis. So when you see that, that automatically tells you that you're going to end with a dy, which means your equations need to be written with the y in them, and we have to rewrite that if needed. Okay? It also indicates that your bounds have to be in terms of y, right? So what's the lowest circle? It's 1. What's the highest? It's 8. So notice all of those highlighted pieces are written in terms of y. And then the only other error that you see quite often is a lot of students forget about pi, right? And notice how pi is in my answer. Just leave it as pi. Don't do 3.14. That would be a big error because we're rounding there incorrectly. So that's what we got. If you have any other questions, please make sure you watch the video from last Friday. Mr. Waffler goes over a handful of problems like that. And your homework tonight is 8.2 day 1 right here. These problems are written out and the answers are posted in Schoology. So please check your work as you go along, giving yourself confirmation that you're doing it right. All right, have a good one. Adios.